Namaste and welcome back to JEE Physics with Typical Monk. This is class 2T7, Nuclei. Deep inside the atom sits the nucleus, 100,000 times smaller than the atom itself, yet holding nearly all of its mass, packed to an unimaginable density. And it hides a quiet secret. A nucleus weighs a little less than the sum of its parts, and that missing mass, through Einstein's E equals mc squared, is the binding energy that holds it together. From that one idea flow the sun's fusion, the reactor's fission, and the steady tick of radioactive decay. Today, mass defect, the binding energy curve, radioactivity, and the decay law. One idea at a time. Here is what you will master today. First, nuclear size, density, and mass defect. Second, binding energy, and E equals mc squared. Third, the binding energy curve, fusion and fission. Fourth, radioactivity, alpha, beta, and gamma. And fifth, the decay law and half-life, one idea at a time. Let us set the foundation. The nucleus, tiny and incredibly dense. It holds the protons and neutrons in a space 100,000th of the atom. Mass defect. A nucleus weighs slightly less than its parts, and that missing mass became the binding energy. E equals mc squared. Mass and energy are one, and a tiny mass releases an enormous energy. Master line, the binding energy per nucleon decides which way nuclear reactions release energy. Now look at the picture, the binding energy curve. The curve plot the binding energy per nucleon against the mass number, and it rises, peaks, and falls. The peak, iron near mass number 56, is the most tightly bound, about 8.8 mega-electron volts per nucleon. Fusion, light nuclei to the left, combine to climb the curve, releasing energy. Fission, heavy nuclei to the right, split to climb the curve, also releasing energy. Now the size, the density, and the mass defect. Nuclear radius, R equals R0 times a 2 the 1/3, the radius grows as the cube root of the mass number. Constant density. Since the volume grows as the mass number, the nuclear density is the same for every nucleus. Mass defect. The mass of the nucleus is less than the sum of its nucleons. Binding energy, that lost mass, times c squared, is the energy binding the nucleus together. Now radioactivity. What it is? An unstable nucleus decays, emitting radiation to reach a stabler state. Alpha decay, it emits a helium nucleus. The mass number falls by 4, the atomic number by 2. Beta decay, a neutron turns into a proton, or the reverse, and the atomic number changes by 1. Gamma decay, a high-energy photon from an excited nucleus, and there is no change in mass or charge. Penetration. Alpha is the least penetrating, gamma the most, and alpha is the most ionizing. Now look at the picture. The decay law. The law. The number of nuclei fall exponentially. N equals N0, e to the minus lambda t. Half-life. The time for half the nuclei to decay, and every half-life halves the amount again. The decay constant. It is lambda, and the half-life equals 0.693 over lambda. Activity, the rate of decay, which itself falls exponentially with time. Now what all this releases? The energy. Mass energy. Einstein's E equals mc squared ties the mass defect to the binding energy. Fusion. Light nuclei fuse, as in the sun and the stars, releasing vast energy. Fission. A heavy nucleus splits, as in a reactor or a bomb, releasing energy. Why both release energy? Both move toward the peak of the binding energy curve. The scale. A nuclear reaction releases about 1,000,000 times the energy of a chemical one. Now the formulas that earn marks. Nuclear radius, R equals R0 times OT RE forme. Decay law, N equals N0, e to the minus lambda t. Half-life, it equals 0.693 over lambda. Now match each formula to its meaning. R0 times a to the 1/3 goes to the nuclear radius. N0 e to the minus lambda t goes to the decay law. The binding energy peak goes to iron near mass number 56. And alpha decay goes to the mass number falls by 4. 4 pairs, each worth memorizing. Now, how many of these statements are correct? Statement 1. The nuclear density is the same for all nuclei. Correct. Statement 2. The binding energy per nucleon is highest for the heaviest nuclei. Wrong, it peaks near iron. Statement 3. A half-life halves the number of nuclei. Correct. So the answer 2 are correct. Statements 1 and 3. The trap is the heaviest nuclei peak in statement 2. Now the 2 mistakes that quietly cost marks. The truth, the binding energy per nucleon peaks near iron, and both fusion and fission move toward it. The trap, thinking the heaviest nuclei are the most stable, the peak is at iron, not uranium. The second truth, the nuclear density is constant since the radius grows as the cube root of the mass number. The second trap, confusing the half-life with the mean life. The half-life is 0.693 over lambda, while the mean life is 1 over lambda. Now, test yourself. Answer in your head before the reveal. That is how G speed is built. Here we go. Question 1. The nuclear radius. R0 times a to the 1/3. Question 2. The decay law, N0 e to the minus lambda t. Question 3. The binding energy peaks near iron, mass number 56. Question 4. Alpha decay lowers the mass number by 4. And question 5. The half-life in terms of lambda, 0.693 over lambda. Let us gather it all in one breath. The nucleus, tiny, dense, and of constant density, R equals R0 times a to the 1/3. The mass defect and E equals mc squared give the binding energy. The binding energy curve peaks at iron, and fusion and fission both release energy. Radioactivity, alpha, beta, and gamma. Alpha least penetrating, gamma the most. The decay law, N equals N0 e to the minus lambda t, and the half-life is 0.693 over lambda. Next class, semiconductors, energy bands, and the p-n junction. A little mass, a vast energy. The nucleus keeps its promise in mass, weigh its parts, weigh the whole, and the tiny difference through E equals mc squared is the binding energy that holds it together. Iron sits at the summit of the binding energy curve, and everything else, light or heavy, releases energy by climbing toward it. The sun by fusion, the reactor by fission. And when a nucleus is unstable, it simply decays, halving with every half-life. Next class, we leave the nucleus for the crystal, semiconductors. Sarah, David, Lisa, and John all began exactly where you are sitting now. One idea at a time. You will crack G. I will see you in the next class.